Okay, so today we're going to look at chapter 4, development of beam equation. In chapter 4, we will look at 3 items. First, we will look at stiffness matrix again, but this time we'll look at beam, and then we will look at assembly of beam, and then we will do analysis using a direct stiffness method. We'll look at concentration force and distributed force. So we look at 2 scenarios. Yeah. Okay. So what is how do we already define what is beam already. So yeah, so this is the textbook definition. You can download the chapter 4 tutorial question. It's already available on the Moodle, so you can download while you're following through the lecture. So what is beam? So beam basically consists of a structure member that you have a loading at both ends, then it will behave under loading. So as what you see on the screen here. So let's say you have a structure member. Before loading, you'll see a straight line. So after the loading on the member, so this structure, it will behave under the effect of the loading. It might be experiencing bending and also twisting or axial effect. All right. So again, this chapter, we will look at 2 effects. One is bending, one in twisting. Yeah? So axial effect, what I mean by axial? So for example, if you have a tube or a cylinder, so let's say you are having x-axis and y-axis. So if you have a pulling force in along x-axis and it is at the center of the cross-section, let's say you have a tensile force, you have a positive force at both ends, you get a tensile force. So under tensile force, you know that if the tensile loading or the force acting on both ends is within the elastic region, modulus Young, this object is going to elongate. Okay, this object going to elongate. That's why you have a delta L that allow you to calculate the strain. The strain. Strain is a deformation of your length. You take the change of length divided by total length. Then you calculate the strain. Okay, so this is the actual effect. Actual means you along the axis. What happened along the axis is called axial effect. So this chapter or chapter 4, when you're told to do analysis, we'll only look at 2 effects. Again, we'll look at bending effect and twisting effect. So if you look at the member of the solid line here, this is the beam that under the loading scenario. So let's say we will have F support, right? We have a F in Y direction. So at this point, you should already understand when you have a notation of F1Y. What I mean by F1Y? It means force. And if you see a capital F here, you already understand that it is an element. Yeah, this is a element force. And if you see a capital F, it means it's a global force. So at this point, we already covered in chapter 3. You know what is element, what is a local force or local element, what is a global force. So if you're seeing a small f, it means it's an element. 1 means 0.1 or node 1. Y means in y direction. Yeah. So you have, if you have, let's say you have an axis, x, y, and z axis, x, y, and z axis. So all the displacement in x, previously we use u. All the displacement in y, we use v. All the displacement in z, we use w. All right. So in this case, or in chapter 4, we will look at vertical component. Yeah. So vertical component, we will use v, and then you see a notation 1 means is referring to node 1 or location number 1. Okay. So this also explained when we have a vertical direction means we will look at v v notation. Okay, and then we have a moment. If you see a arrow, a anti-clockwise moment, so you'll use M1. It means it's a moment. It's a twisting moment at point 1. And you see there's a phi. Phi means there's a twisting, angular moment. You have one moment here, and then there's a twisting behavior. We use phi, and you see a sub 1 means referring to node 1. Okay, apply the same for point 2. You see the small f, 2y, and v2, and also m2 and v2 or pi 2. So okay, what else? Okay, the direction of moment. The direction of moment is anti-clockwise positive for moment. Yeah, you see all the arrow here. We assume it is positive. All right. So I'm going to ask question. Okay, Katana, what is the direction of moment when we consider positive? Katana? Katana, are you there? Let me text here. We consider a positive moment. Lai, you there, right?
Yes.
Okay.
I'm here. It's just that my mic has issues, but anti-clockwise for positive.
Okay.
And yeah.
Okay. All right. Okay. So we continue. So we will have bending deformation. Bending deformation is measured as a transverse displacement and a rotation. So we will have a displacement. In this case, we use the textbook word displacement described by transverse. Transverse displacement, which is in the vertical form in this way, and a rotation. So later on in your matrix, you will see a displacement and a rotation plus a moment. So it will be a very big matrix. It will be a very big matrix. Okay. So if we have if we write vi, a small vi means location notation. If you have a vi, it means it's a local transverse notation displacement. So in this case, previously in chapter 3, all your displacement is in u or v and so on. In this case, in the chapter 4, if you consider beam, we will look at y component only, Vi. All right, Vi is a nodal displacement, and the pi of phi here, it is transverse nodal rotation. So again, we focus on displacement and rotation in this chapter. The rest you are familiar. What is F? Small f is a local. If you look at a capital, if you have a capital F, means it's a global force. If you have a small f, it means it's a local, referring to the element. We have a bending moment, m. Again, definition, what is moment? If you have a point, if you have a point x here, and you have a force, the products of the distance perpendicular to this point, the products of F cross D, you'll get moment, yeah? So it must be 90 degrees to create a moment direction. In this case, you'll get a negative moment because we assume all moment positive is anti-clockwise. Okay, remember, we assume for this chapter, we assume all the moment anti-clockwise is positive. Okay. So we're looking back at the same diagram again. We have a beam that under local force at point 1 and point 2. We will have a local transverse nodal displacement. We have a transverse displacement. We have a transverse rotation, and then we have a bending moment. So again, this is a note. Our bending moment or moment in our structure here will be positive when it is counterclockwise or anti-clockwise direction. Notation for local transverse rotation or the twisting effect is positive when it is anti-clockwise also. Yeah? So the moment and the twisting effect or the rotation, transverse rotation, it will be anti-clockwise when it's positive. Yeah. So again, moment and rotation is positive when you are having an anti-clockwise direction. However, for transverse, we will follow the axis. Yeah. Force also, we will follow the axis. The force, the local nodal force, we will follow the y-axis, where if it's going up or along y-axis, vertical, we will have positive. And then the local displacement or local transverse nodal displacement. Chapter 4, we will purposely mention the word transverse because it is beam. This is beam, it's not bar. So beam is having a transverse displacement. So it will be positive when we have a y direction. Okay, I hope you will be very clear on the notation, because later on when you do a calculation, the direction will affect the positive and negative sign. All right, so be clear of the direction. Which direction give you positive, which direction give you negative. All right, so again, for moment and rotation is anti-clockwise. For force and displacement will be along the axis y. Right, it will follow axis y to be positive. Okay, I think this one is quite straightforward. We move to next slides. So we'll look at one example. So let's say you have a beam, and this beam, if you look at the diagram, you're having a moment on the left and moment on the right, and you have a transverse displacement. On the left is going up, on the right is going down. So you are having a by looking at this diagram, you should know which one is positive, which one is negative. Yeah. Okay, so Lai, this question is for you. What is the signage or what is the notation for, I'm asking about notation positive or negative here. What is the notation for, let's say I name this one is 0.1. This is 0.2, yeah. What is the moment notation? Or this moment, it is positive or negative based on our assumption?
Negative,
Negative. Why?
because the direction is clockwise.
Clockwise, yeah, correct. Okay, Katana, this question is for you. What is the signage or what is the notation for your displacement of this component at point number 2? It is positive or negative, and why?
It's negative because
Okay, negative. Why? What's the reason?
it's headed on the negative y direction,
Correct.
y-axis.
All right, excellent. Good. Okay, so at least you know. So now we just show you the conventional sign for shear force and bending moment. So chapter 4, you need to know how to draw the shear force diagram and also bending moment diagram. So on your screen here, the second diagram on the left, the first diagram on the left here. So you are having when you have a beam and we have a distributed load on top of the beam, and you have a 2D case here where you look at A, B, C, D element here. So this one, let's say you have a support on both sides. So you have a force going up, a force going up. And then there's a additional loading on top of the structure here. So for case A, for case diagram A here, we are looking at undeformed, or there is no deformation happen yet under the distributed load here. All right, so I'm going to show you second one. So after sometimes when the load acting on the body, we will have a deformation happen. So the diagram in the middle here, it's showing you a deformed beam, and we want you to focus on the middle section here, where you look at element A, B, C, D. So if you compare side by side, so you look at point A, B, C, D, and A prime, B prime, C prime, and D prime. Okay, so from here you can see that CD have changed to C prime, D prime, and the length is elongated. So in this case, this is elongated. So it's a stretcher, or in normal English, we call it stretching. There's a stretching at the bottom surface here. And for AB, it's getting, it can be shorter or it just remain at what it is. So if you compare A prime, B prime to AB, you are having a compressed scenario for A prime, B prime here, or it becomes shorter sometimes. Okay, so if you again you make comparison with A prime, B prime, the top surface and the bottom surface, there is a difference behavior. One is compressed, one is stretch, or there's you have a tensile behavior below here, and then we apply by this angle. Okay, we have a deformed angle here. We use phi just now. Okay, so this is the we call it local nodal rotation angle, right? So it's a transverse rotation. So these slides will tell you what is transverse rotation. So this is the angle phi here. Okay, and then the third diagram you see on the third diagram on below the screen here, you will see that if you look at element ABCD, or we can draw it in the free body diagram here. You can look at let's say ABCD. CD is dx, right? C prime dx also dx. So we will draw a free body diagram over here. So on the diagram here is quite direct. So you have a shear loading on the left, is going up, and then shear loading going down. So if you under the loading of W, Wx is a distributed load function along X. Yeah, it just means that it's same like you write Fx like that. So in this case, it's a load in the X function. So you're having a load function in a small element, dx. On the left-hand side, you have a v. On the right-hand side, you have a plus dv. Okay, so when we draw a free body diagram for a loading, we will have v on the left-hand side. After it cross dx a certain distance under the loading of Wx here, you will have shear loading, a shear force, plus dv, a little bit of additional of the shear loading, and then you have on the left hand side you have a clockwise moment. On the right hand side you have an anti-clockwise moment plus dm, is additional of moment on the right hand side. So this is how we transform, or how we draw, or the component of a free body diagram for a differential beam element when we look at a beam. When you look at beam, so this is guidelines for you to draw the beam element. So make sure when you draw a beam element free body diagram, you have all these components. You have a shear loading, point 1, point 2. You have a moment at point 1 and point 2, and then the loading. It can be distributed or it can be a focus point. Focus load means you only see arrow. If you have a distributed load, means you see something like this that I draw on the screen here. Okay, so you have two types of load that we will consider for this chapter. This is the focus load. This is a distributed load. Okay, so we'll move forward. So now we're going to start looking at the beam stiffness matrix, and we will look at Euler-Bernoulli beam theory. In this section, we will only consider bending deformation only. Yeah, bending deformation only. Okay. All right. So again, we look back at the diagram just now. So let's say we have a beam under a distributed load here, and we're having a support at both ends. And we look at element ABCD again. So this case is no deformation happened yet under the first diagram on the screen here. Then we have a deformed scenario with a this twisting angle. And then recall back what we covered just now, the free body diagram for our beam element. Again, in this case, we only consider bending deformation. So I think this one you can read from the slides here. The Euler Bernoulli beam, we're looking at the linear elastic beam. Linear elastic beam means it's agree to the Hooke's law, or it will, when you pull the beam, the elongation delta L will follow a linear equation of your loading. So it will agree with the modulus Young limit. So we only consider up to the elastic limit here. We will not consider after it break, yeah. So we will only consider up to modulus Young limit or maximum elongation here. So in this case, we will consider we are having a Euler Bernoulli beam structure. Okay, so in your test or exam, when you see the Euler Bernoulli beam is mentioned in the question, it means that we only consider within the elastic region of your structure. So a few textbook or terms that you should be start familiar with when you start studying chapter 4 on beam. The first is plane cross section. Plane cross section. So you know what is cross section, right? So perpendicular to the central axis. Longitudinals means if you have an x, right? So you know that okay, the rest I think you can read from the screen here, yeah. So it just means that the cross section will change from longitudinal within the bending effect, yeah, within the bending effect, as you can see on the screen here. So you will see that there's a change of plane, this one, and you see that there's a change of angle of your AC. So from AC to A prime, C prime here, you see there's an angle. Okay, you just explain what is bending. Yeah. Okay. So if you look at AC, the line AC is perpendicular to the longitudinal x-axis before bending, which means longitudinal axis, which is this one, your x-axis. So if you enlarge your AC, the x-axis is 90 degree, which is perpendicular, and this is the cross-section area of this element. Okay, the cross-section is perpendicular, and then it will remain perpendicular to the bend x-axis after bending. What does it mean? It means that if you look at the plane here, the axis actually is bending like that. You have a curve, right? You have a curve of your x-axis. Your x-axis is no longer straight line, so however it is still a curve. So the cross section still perpendicular to the your longitudinal axis. This is what it means on the slides here. All right, and then we look at the free body diagram over here. Then we need to balance all the force and moment equal to 0, or the word equilibrium. Again, here we focus on force and momentum. So the equation for this case, if you look at this free body diagram, we don't have x component, but we have a y component. So all the force in y component is, okay, see, this is capital V, yeah? Capital V in this chapter or in this diagram here is a shear loading. It's a shear loading, it's not a velocity or it's not other term, it's a shear loading. Shear loading or shear forces. Again, recall what is the name shear and normal load that we defined previously. Let's say you have a cross-section area. If you have a force that, this is the force, if you have a force that 90° to the area, this case is normal forces. So if this one is stress, then become normal stress. If your force is going parallel with the area, your force in this case will become shear force. Or if this component, this vector is stress, it will become shear stress. The important concept is the relationship between the vector and the area. If it's parallel to the area, or moving along area, it becomes shear force or shear vector. If it is normal or 90° to the area, it will become normal force. In this case, if you look at the diagram, the force is going parallel to the area here, parallel to the area here, meaning if you have a plate like this, this is the area. So if you have a force that go parallel to the area here, you have a shear force like that. Okay. And if you cut a metal, normally the machine will use shear loading to cut metal. If provided the metal is very thin, yeah. It's like a scissor. If you cut paper with your scissor, it also apply shear loading to the object. Right, so the concept shear is very important, yeah. Shear and normal force. Make sure you recall back what is the definition of shear and what is normal. All right. So if you write the equilibrium equation for all the force in y direction, so you take V plus this component. Right, on the left hand side is positive. On the right hand side, because it's going down, y-axis. Right, again, throughout the global axis. So this loading, V again is not velocity, it's a loading. So if you see V means it's a shear loading, it's going down, means you get a negative sign of this whole component. So you will get, and also we plus the loading on the structure, Wx. Wx, what is W? W is the distributed weight, which is in the unit of Newton per meter. So you want to find, if you want to convert distributed weight into useful load, or W, equal to small w times the distance of the length. All right. So if you have a distributed load on a structure and you have a length of a structure, so if you're given a W, let's say you are having the W, maybe you're having a 10 Newton over meter. The length is maybe 2 meter. So the loading on this object will be W equal to 10 times 2. You will get 20 Newton acting on the object. And of course, you learn in your static or dynamic, you can transfer or assume that your distributed load become a focus load, and you need to find the location of the focus load. You can convert distributed load, assume as a focus load. So before you assume as a focus load, you need to take the small w times the L or dx. You get the loading on the structure. Okay, so that's why you see in the equation here, you see that when you sum up all the force in one direction, you have V minus the product of V plus dV, which is this side, minus, this is going down, W times the dx equals 0. Yeah, so you should be able to understand why W times dx here, because W again is Newton over meter times meter. Yeah, so I'm doing dimensionless analysis here so that you know at the end you still get Newton. Yeah, the unit of V here is Newton. This is also Newton minus Newton. You get in Newton. Yeah. Okay. Then, if you summarize the equation above, this one cancel this one. You have minus dV minus W dx. So you get the simplified equation over here. And you can write what is your W. W, you move this one to the left, you get positive. However, the negative sign here, you move to the left, you carry together, divide by dx, you get your distributed load equal negative dV over dx. So this is the first equation we define for your W. Yeah. So your W is the differentiation of your shear loading, but is in the negative position or negative arrow. Yeah, we disagree with this free body diagram. Yeah, your W and V. W is the distributed load. V is a shear loading, so it's a different direction. You do the same for moment. So moment on the left is clockwise, so you write. Okay, so this is how you calculate for moment. For example, if you write all the moment at point 2 equals 0, so you focus on point 2, you stand at point 2, all the moment at point 2 will be ignored and all the force will be ignored. Then you look at what are the force that you have that create moment. So the first one is your the change of moment here. So you take negative V times the dx. Negative, why negative? Because if you only consider the V, the shear loading is this direction, and you have a dx here. Again, this one, dx and your V is 90 degree, and you're standing at point number 2, you will create this effect, this combination, V dot dx will create clockwise moment. So again, clockwise is negative, yeah? Clockwise moment, it become negative, so you get the first one. How you get dm? If you cancel out, you take the m plus, you take the m plus dm minus m, so you get the net moment that you have on this element. All right, so you know that moment is moment clockwise is negative, clockwise, anti-clockwise is positive. So you take this positive term minus m, you get dm. That's why you get the second term here. And then how you calculate this term is that you transfer. Let me draw something on the screen here. So let's say, again, this one you need to call back what you learned in your static or dynamic module. Wx, again, is a distributed load in the unit of Newton over meter. So you need to convert into focus load with this big W. So how you get big W is that you take the small w times the length, or in this case is dx. All right. And you're standing at point number 2. You're looking at moment at number 2. So this focus loading will create a anti-clockwise direction. All right. If you look at dx is 90 degree to the loading here. So this effect will create anti-clockwise moment. So again, anti-clockwise is positive. So again, sorry, I give you the wrong notation here. The distance is dx. If you convert from distributed load to a focused load, in this case, it will always will take the half length of the element. If your distributed load acting along the whole element here, then the distance, when it convert into focus load, the distance will be half. So dx divided by 2. So the products of moment at point number 2, the moment that created when you stand at point number 2, you take w times the big W, or the small w times dx, times dx divided by 2. That's why you get this term. Okay, so clear? Katana and Lai, you understand how you get this term? Katana, you clear of this equation?
Yes.
Okay, Lai, you okay with the equation?
Okay.
Okay, yeah, right. So these two fundamental principle is important when you try to solve a question in coming test or your coming exam. Yeah, so it is important how you get these two equations when you derive from the free body diagram over here, right? Right. So the next one we will simplify further this equation. Right. So again, there's a note. When you divide left equation with dx, we want to remove all the dx here. And then we take the limit of the equation as the dx approach 0. Yeah. So this one will be 0. Yeah. This one will be 0 when we do the cleanup steps for these terms. So this moment 2 equal to 0, at the end, we will arrive at your shear loading will be equal to negative dm divided by dx. Yeah. All right. So we have some mathematical procedure or treatment over this term here. Yeah, by this note over here. Okay. All right. Okay, so we look at equilibrium of your force and moment at this stage. All right, let me stop the recording.